So Gauss's law. We've been using Gauss's law to derive equations for electric field. We did it for spheres yesterday. It is useful if you can draw your imaginary surface, your Gaussian surface, that includes the point you're interested in, but so you can draw it so that the electric field will have the same value everywhere on the surface, and so the electric field will be parallel to the area vector. Another example where we can use Gauss's law is to derive our equation we have for a large plate or plane of charge that has a surface charge density eta. So let's pretend we have a large plate that's positively charged. What will the electric field look like around this plate?
Straight out.
Straight outwards. So it'll be coming out on these sides and on this side. Now, Gauss's law will, in terms of finding electric field from Gauss's law, it does not work well around sharp corners and sharp edges. So we would not be able to find that, use it rather, to find the electric field near the edges of this sheet. But it will work as long as we stay in the central region, where we're not near the edges. So we need to draw a surface. A sphere is not going to work. Okay? Even though the electric field would have the same value, the electric field vector would not be parallel to the area vector. So we cannot draw a sphere and use this same setup to find the electric field. What shape do you think we could draw so that the electric field will have the same value everywhere as it passes through the surface, and so the electric field will be parallel to the area vector? It needs to be three-dimensional though. A cube would work great. That's my attempt at 3 dimensions. So the electric field will only be coming through these end faces. The sides, there will be no electric field passing through. You alright with that? So there's no electric field lines passing through the lateral sides of this cube, only through the two faces. So flux, the electric field is parallel to the area vector because the area vector points outwards there. The flux is going to be the electric field times the area that the field lines pass through. If we call this length L, since we're using a cube, the area will be L squared, but the field lines are passing through both ends. So there's 2 L squareds. So our area is 2 L squared. Our other equation for flux, charge enclosed over epsilon naught, we need to figure out how much charge is inside this little cube. We can do that by way of density. We know surface charge density is charge per area. So the charge inside of this little cube is going to be the surface charge density times the area inside. The area that's cut out by the cube. So the charge enclosed is eta. We already labeled the sides as L, so the area is L squared.
Just for clarification, the L squared, you don't square the 2 as well.
No, because there were 2
Times
L squareds. Yeah. Okay, setting these equal to each other. Turns out the L squareds are going to cancel. That leaves us with E being eta over 2 epsilon naught. I already gave you that equation when we were talking in chapter 27. but this is an easy way to derive it. Easy way to come up with the value. So this electric field works as long as you're near the central regions of the plane. As long as you're not near the edges. It won't work near the edges. So we would say this was valid for a very large plane or plate. Either way. So Gauss's law works well for spheres, and it works well for very large other shapes, as long as you don't get near the edges.